And Mohan is probably the closest to a Renaissance researcher that exists these days, with interests ranging from communication complexity to exact algorithms per set to social networks, computational economics, and even academic publishing. So, and beyond computer science to pretty much everything else. So while Mohan's here, you should take advantage of him and talk to him about pretty much anything.
Okay, thanks, Russell. So my latest research topic is cellulose, and what are they good for the body? Now, how are they good for the body? And so I'm kind of working on nutrition now. Okay, so this talk is about exact algorithms and complexity. It will be, I will try to give you, since most of you are not working in this area, it seems that I could give you a slow introduction and survey some of the key developments in the field, and finally talk about the new result about circuit complexity, circuit satisfiability complexity. Okay. So this is outline. So we talk about exact algorithms with some definitions and some of the dramatic recent progress made in developing better algorithms for NP-hard problems, and we will see some of the beginnings to baby steps taken to develop the develop the complexity theory of exact algorithms, and we look at the recent result about circuit sat. So let me start with something familiar to all of you, which is the parameterization. Before we define exact algorithms and non-trivial algorithms, we need to have the right parameters in mind. And so we are looking at problems in NP, specifically it's NP complete problems, and these problems come with two parameters. One is the size of the problem, and the second, which I call the complexity parameter, is the size of the witness. Okay. So when we talk about an NP problem, we will explicitly mention the complexity parameter that we have in mind, that we are going to look at. So so there are many choices for the complexity parameter, and so it's important to explicitly specify and talk about its talk about relationships among various parameters. Okay. So okay. So given that we have this parameter p of x, which basically is the measure of the set space where we can find the witness. Okay. Now we can talk about what are the trivial exact algorithms. These are the algorithms where the worst case time complexity is bounded by 2 to the px times poly in the size of the input. Okay, so most of our algorithms will have the following format, which is some exponential in the complexity parameter or the witness size times poly in the size of the input. Okay. So what is non-trivial exact algorithm? Something is non-trivial exact algorithm provided we can improve the exponent even by a tiny bit. Okay. So mu is the improvement factor here, and mu can depend on the class of the instances we are dealing with. For example, if you are talking about k-sat or kcn of sat, mu could depend on k. Okay. So these are also known as moderately exponential time algorithms or improved exponential time algorithms. And this talk is about this is about improved exponential time algorithms. So let me give some examples to make sure that that our coordinates are set properly. So take the well-known traveling salesperson problem. So we are given a graph and weights as well, or we can look at the simpler Hamiltonian path problem without weights. And we have two parameters for complexity. For example, the number of edges and the number of vertices. The problem size itself is the adjacency, so the description of the input length. Okay, and so if we take the number of vertices as the complexity parameter, okay, and so the first okay. So if we take the number of edges as the complexity parameter, so you can see the first dynamic programming algorithm. So that was obtained in 1962 as a non-trivial exponential time algorithm. Okay, so the number of edges. Okay, I'm sorry. So let me start again. So in the traveling salesperson problem, so we are looking at the longest path, and so the search space is over all permutations of vertices. So therefore, if you take the complexity parameter as a log of n factorial, so this dynamic programming algorithm is the first non-trivial exponential time algorithm. So since then, no progress has been made on this problem, and no one knows of any better algorithm better than 2 to the n. So in other words, can we find a non-trivial exact algorithm that is when the complexity parameter is the number of vertices? Okay. So let me give another example, which is the K-SAT. And here you have a formula with clauses where each clause has at most k literals, and n is the number of variables, and there are at least 2 choices for the complexity parameters. One is the number of clauses, one is the number of variables. Okay, and it turns out the number of variables is a more natural choice, and it turns out that they are roughly equivalent as far as sub-exponential time is concerned. So we will take the number of variables as a natural complexity parameter here, and there are several non-trivial algorithms have been developed over the past 15 years, and they are all of the form 2 to the n times some constant, which seem to be growing to 1 as k goes to infinity. Okay. So let me talk about some obvious questions and here. And so let's define the sub-exponential algorithms class as those algorithms that can be solved in time Pauli in the size of the input times 2 to the epsilon times the complexity parameter, where epsilon can be arbitrarily small. Okay. So one of the obvious open questions is that well-known question is that can we find sub-exponential time algorithms for 3-SAT in particular? Okay. And if not, what's the best possible exponent? Okay. So there are many different motivations for studying exact algorithms, and so let me quickly list them. And sometimes you want exact solutions, so approximations are not good enough, and sometimes it's hard to approximate problems, like for example independent set. So you can't get good approximations in polynomial time. Okay. And the third reason, basically the small improvements in exponent can increase the range of feasible instance sizes. So for example, a SAT algorithm or a 3-SAT algorithm of the type 2 to the n over 1000 could have a significant impact in practice. Okay. So there's clearly a motivation to see what's the best constant we can obtain for solving these problems. Okay. So, and it turns out that in this quest for designing better algorithms, people have discovered many interesting techniques and analysis techniques as well, and so that itself is one reason to pursue this study. From a complexity point of view, I'll tell you more about this, and studying this exact complexity might enhance our understanding among the relationships among these problems. And finally, one challenge here is that there is a whole community of heuristics, people who develop heuristics and implement them. And they have shown spectacular success on seemingly hard problems, including traveling salesperson. Okay. So the question is that they can solve instances of 10,000 or sometimes even 100,000 variables. Okay. So the question is that for what class of instances do they work well, or can they produce? Can they terminate in a feasible time and produce correct answers? And what are the hard instances on which these heuristics might not work? Okay. So that's fairly open area. Not much understanding has been gained. So this is a constant race. The people from the heuristic community keep inventing new heuristics and keep implementing them. Sometimes show a spectacular success, and the scalability of those algorithms and the scalable behavior is still a question. And okay. So let me quickly go through a sequence of results for some of the problems to show kind of how much effort has been put into developing better algorithms. Maybe since the middle of 1980s, while some of the early algorithms have been developed in 60s, since the middle of 80s, people have started looking at these exact algorithms and came up with a series of algorithms. And one of the first problem is maximum independent set. So given a graph, and you want to find a maximum independent set where the complexity parameter is the number of vertices. Okay. So so you can see the series of improvements, and the standard technique here is the pruning the search tree. Okay. So you branch and then you reduce the number of cases, and then you reduce the instance size of the instance, and then obtain a better recurrence relation. Okay. Sometimes the case analysis can be quite hairy. For example, that 2 to the 0.25 and Robson result has not been submitted to a journal, and it has not been fully verified. Okay. So it's an 18-page partially computer generated proof, and it looks at several hundreds of cases to obtain the better bound. Okay. So right now the verified bound stands at 2 to the 0.287, and that uses a new technique called measure and conquer. It's the same algorithm, similar algorithm to the previous ones, but they look at the instances and measure the complexity of the instances. So using smarter techniques and come up with a simpler analysis. And for sparser graphs, for example, for cubic graphs, or when the average degree is 3, much better algorithms are known. Okay. So one question that raises this is that is it possible to continue the improvement? Okay. So let me show the other problem where myself and my colleagues have worked on. So this is the KSAT problem, and literally several dozens of papers have been written about 3-SAT. Okay. So this kind of summarizes the progress in the exponent for small k, 3, 4, 5, and 6. And so for 3-SAT in particular, so the best known algorithm has exponent for the special case of unique KSAT, and for the more general 3-SAT, 0.404 is the best known exponent. But I did hear that someone has recently improved the third decimal of that result. I don't have the reference at this point. Okay. So, but all these results have the following format. So the exponents seem to be decaying and seem to be increasing to 1 as k goes to infinity. Okay. So that's so that expression 2 to the 1 minus mu k over k minus 1. So that's the best exponent known. So at this point. Okay. So let me give the next the most recent dramatic success. This is the graph coloring problem to Tut polynomial. Okay. And So just like KSAT and traveling salesperson problem, so this problem has been studied for a long time. Lawler is one of the first people to look at the computation of chromatic number, and he came up with a 2 to the 8.6 to the power n algorithm, and more recently surprisingly using rather than dynamic programming, so using the technique of inclusion exclusion, people have come up with the breakthrough result of solving the chromatic number problem in 2 to the n time and exponential space. Okay. So that kind of whereas inclusion exclusion has been used to reduce the amount of space. So CORP has used inclusion exclusion to come up with small space algorithms and to improve for Hamiltonian path. So these results show, in particular, the dramatic power, and several people have tried to improve the chromatic number to 2 to the n, and this is the first time that this technique. These results have shown made significant progress, and even the Tut polynomial can be computed in 2 to the n time and space. And if you want to do it in polynomial space, you have to suffer small degradation. And on the other hand, so if you look at specific problems like 3 colorability or 4 colorability, so you can get much better exponents. But on the other hand, not much has been known. Much better algorithms are not known for problems like 5 colorability and 6 colorability. So the best known at this point is 2 to the n for all k. Okay. So the list goes on here. So those were the 3 important cases, and a number of problems have been looked at: dominating set, tree width, max cut, feedback vertex set, and so on. Okay. So more importantly, the range of techniques is quite large, from the pruning the search tree, which is a Davis-Putnam style algorithm, to standard dynamic programming, to local search Schoning's algorithms for 3-SAT, and better analysis technique like measure and conquer, and then more recently the inclusion exclusion principle, and color coding, which can be used to obtain better algorithms. Okay, and group algebra techniques, and even matrix multiplication can be used to improve the exponent for exact algorithms. Okay, that's due to Ryan Williams. Okay, and then we have the more traditional exponential time divide and conquer techniques that have been used to obtain better algorithms. And for the shortest vector in the lattice problem, sieve algorithms have been used to obtain better exact algorithms. Okay, so this is a range of techniques, So one can kind of summarize this development in a couple of sentences. Okay, while we know that all NP-complete problems are equivalent as far as polynomial time solvability are concerned, so we see that so these results show that there is significant variation in the worst case algorithms in terms of better exponent. Okay, so and it's also clear, at least for some problems like KSAT and independent set, the progress seems to have slowed down and came to a halt in terms of improving the exponent. Okay. So where do we go from here? Okay. So what's going to? Okay. So this raises a number of questions, and so for what problems can we expect improved algorithms? For example, why can't we get an improved algorithm for Hamiltonian path when the number of vertices is a complexity parameter? So this has defied progress. So this problem has no one has cracked this problem. Okay, and whereas coloring and even Tut polynomial can be computed in time 2 to the n. Okay, so a more interesting question is that can these improvements lead to smaller and smaller exponents? Can we expect sub-exponential time algorithms for K-SAT, for 3-SAT, or for 3 coloring. Okay, the series of improvements kind of led one to hope for sub-exponential time algorithms. Okay. So if sub-exponential time algorithms are not possible, can we prove a specific constant lower bound for 3-SAT or for 3 coloring? So that so 2 to the 0.386 is the best constant for 3-SAT. Okay, can we prove that? Okay. So if we can't prove either one of or either of the if we can't prove any of those above, can we at least connect the complexities of these various problems? For example, if we can improve K coloring from 2 to the n to C to the n, where C is less than 2, would that give better algorithms for K-SAT or vice versa? Okay, clearly, there are good reductions between these two problems. Can they help in terms of improving the algorithms from one to the other? So the reductions I'm talking about, the many one reducibilities, which may not necessarily help in terms of preserving the complexity parameter. So therefore, the results would not follow from the well-known reductions. So one has to either find better reductions or find some other technique to connect these two problems. Okay. So these 4 questions can be seen as the goals of the exact complexity theory. So basically, to guide the community that is developing algorithms in terms of what might not be possible and what is possible, and especially giving some guidance where to look for progress. Okay. So let me give you some idea about some of the baby results or the baby steps taken in terms of developing a complexity theory for these exact algorithms. Okay. So the first result is kind of looks at the question of whether sub-exponential time algorithms are possible for the well-known questions like 3-SAT and 3 coloring, and then basically it relates these questions together. Okay. So what it shows is that if any of the problems in SNP are in sub-exponential time, so then whole of SNP is in sub-exponential time. So let me explain these terms okay. So you know what sub-exponential time is, and SNP is the class of those NP problems, subclass of NP problems, which can be expressed by means of a second-order quantifiers, followed by first-order universal quantifiers, followed by a Boolean formula. So for example, independent set or K-SAT or 3 coloring, they all can be shown to have this kind of structure. Okay. So what this result shows is that if you take any complete problem in this class, complete with respect to sub-exponential time reductions, so that's what SERF stands for. So then if a complete problem is in sub-exp class, so then the whole of SNP is in sub-X class. Okay. So what this really means in practical terms is that the fate of sub-exponential time algorithms for the problems like K-SAT, K coloring, as well as independent set, K-SAT cover, and other problems are related, and so they're all one and the same. Okay. So if one of them has sub-exponential time algorithm, so then all of them have. Okay. So let me briefly talk about what techniques have been used to prove this result. Okay. So the key tool is the sparsification lemma, which has found applications, several applications. Okay. So the main problem in proving these results is that the many one reductions that we are familiar with would not preserve the complexity parameter. So for example, if we take a 3CNF and reduce it as a 3 coloring problem, and the number of clauses will become the number of vertices, and a 3CNF might have n cubed clauses. So therefore, you don't preserve the size of the parameter, and therefore you can prove sub-exponential equivalence. So what the sparsification lemma shows is that a 3CNF can be expressed in sub-exponential time as a sub-exponential union of linear size 3CNFs. Okay. So we could by using sub-exponential time, we can get rid of these n cubed clauses and then deal with the linear number of clauses. So once we have a linear size 3 CNF, the reduction to 3 coloring would also result in a linear size a linear size graph. Okay, so then the sub-exponential time equivalence can be seen a lot more easily. Okay. So let me talk about the next and the final result that we know in terms of the complexity of these problems. So let's define S sub k to be the best constant for solving KSAT. Okay, and this could be 0. Okay, so and let S infinity be the limit of these constants. Okay, to make further progress, one approach would be to make a suitable complexity assumption. Okay, and then develop complexity relationships among these problems. So one such assumption is exponential time hypothesis, which states that S sub 3 is bounded away from 0. Okay, and what was proved with this help with the help of ETH is that one of the first result is that S sub k increases infinitely often. So that means for every k, so there is another k prime such that S sub k prime is strictly larger than S sub k. So that means these constants are increasing. This actually this is a non-trivial reduction from a k sat instance to a k prime sat instance, and spacification lemma is crucial. So this lemma also, so this theorem also kind of gives the theoretical evidence to the practically observed phenomenon, so that many of the heuristics developed for 3-SAT do not seem to be working so well for 4-SAT, 5-SAT, 6-SAT, and so on. So things are getting harder, and this theorem is kind of supporting that, kind of assuming ETH is true. Okay. So similar results have been obtained more recently, and so in particular, Troxler has shown that so D2 CSP problem where the variables take D different values should take time d to the c, and where c is a constant independent of d. Okay. So for example, if you look at 2 coloring problem, okay, which is a special case of D2 TSP, so that has a 2 to the n algorithm where 2 is independent of k, but whereas here for the CSP problem is much harder here, and it seems we can do better than d to the n essentially. Okay. So there are many open problems. So even assuming ETH, for example, can we prove a specific lower bound on S sub 3? Can we show that S sub infinity equals 1? Or can we relate the complexity of KSAT and K colorability? Okay. So this is where essentially we kind of stopped, and we couldn't make much progress in connecting these complexities. So what I'm going to talk now in the next 15-20 minutes is the recent progress we made in understanding the relationships among these complexities. So this recent progress is regarding circuit satisfiability, and it raises more questions than answers. So nevertheless, so these are, some of them seem to be new questions. So in particular, so we are talking about finding a connection between K colorability and KSAT and relating the complexities. And that requires finding reducibilities between these problems. And it's conceivable, so these new results kind of give an indication it's conceivable that no such reductions exist. Okay. Part of the reason might be that the kind of techniques we are using or the kind of algorithmic paradigms we are using to solve these problems may be incomparable. Okay. And so there may not be reducibilities among these algorithmic paradigms. And so that's the starting point for the new results. And so one way to make progress is that what we found is that let's focus on algorithmic paradigms people have used to develop exact algorithms. And let's restrict to simpler paradigms and see what we can say about them. And then look at, so that can be used as a starting point to understand more powerful paradigms. Okay. So, so the simpler paradigm that we start off, that we look at is OPP, which is the familiar paradigm, which is probabilistic polynomial time algorithms with one-sided error. Okay, this is basically the class NP, except that we have two resources here. Okay, one is the time, which is polynomial time, and the second one is the probability of correctness. So in the case of non-deterministic computations, it's enough if there is one witness. So what we are interested in is that how well can we guess? So what is the probability of correctness? Okay, so so this class enables us kind of to look at two resources at the same time and possibly talk about the trade-offs between them. Okay, so these Grover's algorithm also speeds up these algorithms. So these class of algorithms, and we can get a square root improvement in the square root improvement in the in these algorithms. Okay. So one of the questions we'll be looking at is what's the best what are the limitations of these algorithms, and in particular we look at circuit satisfiability. Okay. So let me give you some more context here. And we have a number of other paradigms, for example, exponential time divide and conquer, and inclusion exclusion, dynamic programming, group algebra. So none of them seem to be none of them can be converted to polynomial time probabilistic algorithms without significant loss in the probability of correctness. So let me say something more. So if you look at the standard algorithms, standard pruning the search tree algorithms, so Davis-Putnam style branch and bound algorithms. So they all seem to have a polynomial time kernel, and within that time they branch out and then they find a satisfying solution with certain probability of success. And by repeating that kernel several times, so you will get an algorithm that succeeds with constant probability, but in exponential time. And perhaps by using some de-randomization techniques, you can get rid of the randomization as well ultimately. So that will result in a completely deterministic exponential time algorithm. Okay. So what we are asking is that, so let's focus on the polynomial time algorithms with exponentially small correctness probability, and what is the best correctness probability we can get? Question?
Why don't you just define? I think.
Yeah, I will define in a second. Okay.
Define OPP and
okay.
the parameters you're looking. So you'd skip ahead and then come back, I think.
Okay, so let me see. So let me define it right here. So basically, it's OPP is a class of probabilistic polynomial time algorithms, where we have where the algorithms can succeed with are allowed to succeed with exponentially small probability. So that means if the instance is a true instance or a satisfiable instance, so the algorithm must output answer with some non-zero probability. And if the instance is a false instance, it must always say no. Okay. So the question is that what's the best probability of correctness we can get? So that's basically the model.
So non-trivial OPP is one with probability of correctness. So just in your non-trivial time, it was choose some constant mu times the
right.
Was the times the polynomial and the input size was the non-trivial time over exhaustive search. Here, non-trivial OPP means polynomial time in the size of the instance, but with success probability 2 to the minus mu times p of n, where mu is less than 1.
Right, right. So let me restate it with the specific example. So if you take 3 set or 3 coloring or independent set, we can obtain an OPP algorithm by simply a trivial OPP algorithm by simply guessing the subset of the solution and then verifying it. Okay, so that gives a correctness probability of 2 to the minus n. Okay, so that's a trivial algorithm. But many of the known algorithms, non-trivial algorithms that was shown previously, so they can be shown to work in probabilistic polynomial time, giving exactly the inverse of the time as the correctness probability. Okay, so that means if the previously I showed that 3-SAT has a C to the n algorithm, and the same algorithm can be modified to work in probabilistic polynomial time with correctness probabilities C to the minus n. Okay, so the point is that not all algorithms can be converted to work in probabilistic polynomial time with a corresponding drop in the probability of correctness. Okay.
But most of the sort of standard techniques that are used for like SAT can.
Yeah.
Although some of the, so I think what you're getting at is you're trying to say why are the techniques for SAT usually these kind of branch and bound or local search techniques, whereas the techniques for traveling salesperson often are dynamic programming.
Right.
So one possible distinction is that SAT has non-trivial OPP algorithms, whereas TSP, even though it has non-trivial exponential time algorithms, does not have non-trivial OPP algorithms.
Right. So the big distinction between SAT and coloring, or 3 coloring and independent SAT, and the recent K coloring and Hamiltonian path algorithms is that the SAT algorithms essentially came out of OPP algorithms. People started with branch and bound algorithms that work in polynomial time, so then they de-randomized it, okay, or exhaustively searched the tree. But whereas in the case of in the case of K coloring, so we have a 2 to the n inclusion exclusion algorithm, which doesn't seem to, it's not clear how to translate such an algorithm into an OPP style algorithm with a corresponding drop in the probability of correctness. Okay, so the best known algorithm that we have for K coloring is K to the it's an OPP algorithm that can only succeed with the probability of correctness K to the minus n. Simply guess a coloring for the vertices and verify it. That only has a success probability of K to the minus n. So this algorithmic paradigm seem to be the difference between the K-SAT problem and the K coloring problem. So similarly for the Hamiltonian problem, so we use dynamic programming to get the 2 to the n time algorithm, and it's not clear how to translate such a dynamic programming algorithm into an OPP style algorithm with the 2 to the minus n success probability. So the best known algorithm for Hamiltonian path in probabilistic polynomial time only has 1 in n factorial correctness probability. Simply guess the permutation or the path and verify it. Okay. So there seem to be a kind of distinction between these algorithmic paradigms, and kind of understanding OPP might give us. So anyway, so that's. So more generally, so what are the trade-off between probability of correctness and time? So that's what this model, and what are the best techniques to take algorithms from one style of algorithms to another style of algorithms. So for example, we do know that we can take a probabilistic polynomial time algorithm that succeeds with the probability p. We can convert that into an exponential time algorithm that works in time 1 in p, but succeeds with constant correctness probability. So simply repeat the algorithm several times until you get a constant correctness probability. Okay. So the question is that, are there better techniques? Okay. So this talk provides a specific a new technique called exponential simplification lemma that works specifically for circuit SAT. So we'll talk more about that. Okay. And how about techniques that go from exponential time algorithms to probabilistic polynomial time algorithms? So the question is that, can we maintain the optimality in the trade-off? And for Hamiltonian path and for K coloring, we do not know how to get OPP style algorithms with the correspondingly optimal correctness probabilities.
Are there differences in the space requirements for algorithms which are convertible into OPP and those that are
Not quite. So even the K coloring algorithms while the best time bound 2 to the n requires exponential space, there is with a slightly worse constant, like 2.4 to the n, we can do it in polynomial space, probably in linear space. Clearly, in 4 to the n, we can do it in linear space. So space may not be it's not clear if.
So OPP implies polynomial space, but
Right.
not the other direction.
Right. Like with Hamiltonian path, we can do it in a small space in 4 to the n. Actually, in 2 to the n. Okay, so let me quickly talk. Okay, let me give you some of the new results, or let me talk about exponential amplification lemma and show, which basically kind of enables us to show that for certain problems, specifically circuit sat, so even the best OPP style algorithms cannot succeed with probability better than 2 to the minus n, subject to some complexity assumptions. Okay. So let me give some. Let me do a few definitions. So we are going to look at, rather than looking at Turing machines, we are going to look at non-uniform probabilistic polynomial size circuits, okay, and with random bits as inputs, and the complexity parameter is the number of so the number of input bits, and right. So these circuits succeed with certain probability, and they are supposed to be one-sided. Let me skip the definitions and show you the picture. Okay. So the computational model I'm going to look at is that taking circuits as inputs and deciding the circuit satisfiability of the input circuit. So the computing circuit is a random circuit, probabilistic circuit. So that takes random inputs, random bits as inputs, and as well as a description of a deterministic circuit as input. Okay. So the deterministic circuit has two parameters, which is the size of the input and the number of variables. Okay. And we are interested in the probability of correctly computing the satisfiability of the input circuit. Okay. So we are given an encoding. We are given an encoding of the circuit, and we have a circuit family. The circuit family itself is parameterized by two parameters. One is n, which is the number of inputs to the input circuit, and second is m, which is the size of the input circuit. So it's important to make the distinction between the two, and you will see in a second. So we are going to measure the probability of correctness as a function of the number of inputs of the input circuit. Okay. So the circuit C and M has two parameters, n, which is the number of variables of the input circuit. So that n measures the set space in which you are going to find the satisfying assignment. Okay. So we are going to look at the probability of correctness as a function of the set space, and the size of the circuit itself is a function of both the complexity parameter and the size of the input.
So m is the size of the input circuit?
Pardon me?
M is the size of the input circuit?
Right, yeah.
So Mohan, maybe could you flash forward to the statement of the theorem and then
Okay.
go back?
Okay, so let me.
The statement is simpler than the
Right. Yeah, let me just do one more definition, and then I will flash forward to it. So that's the next theorem starts. Okay. So what we are interested in is that what is the best so given the circuit size, what is the best correctness probability we can get. So we are going to scale the probability. Okay, since we are interested in the exponent of the probability, correctness probability, so we are going to scale it, and so we are going to define the complexity of a circuit family for deciding circuit set as a log of the 1 in the probability over n. Okay. So for example, if 2 to the minus n is the correctness probability, so that quantity will give you 1. And if 2 to the minus n over 2 is the correctness probability, so that quantity will give you half as the answer. Okay. So what we are interested in is the complexity of circuit set, when decided by polynomial size circuits. So what's the best constant you can get? Okay. So the smaller the constant, the better off we are. Okay. So so let me now talk about the results. So the first result is that we are going to talk about a slightly more general class than polynomial size circuits, and the technique would allow us to prove results about something larger. So let's look at circuit families whose size is bounded by sub-exponential function of the number of variables and polynomial in the size of the input. Okay. So we have the circuit C and M, and its size is, so since it has two parameters, and its size is bounded by 2 to the little of n times poly in the size of the input, which is M. Okay. And what this result is saying is that, so the circuit complexity is it's either 1 or 0. So that means provided unless NP has sub-exponential size circuits. So either NP has sub-exponential size circuits or the circuit satisfiability has complexity 1.
Meaning there's no non-trivial OPP algorithm.
So in particular, there is no non-trivial OPP algorithm. That means, so the best correctness probability you can expect is 2 to the minus n, unless NP itself has sub-exponential size circuits. Okay. So a somewhat stronger result is that, let us say that your computing circuit is a polynomial size circuit. Okay. So that means the size is bounded by poly in the size of the input, which is M, and again the correctness probability cannot be better than 2 to the minus n. So if it is slightly better, so then we can show 2 to the n to the epsilon or 2 to the n to the mu size circuits for NP. Okay. So let me give another somewhat even somewhat weaker result, but with a weaker assumption here. So let us take quasi-linear size circuits. So the computing circuit C and M is quasi-linear in the size of the input, which is M. Okay. So then in that case, again, the correctness probability cannot be better than 2 to the minus n unless NP has really small size circuits. Okay. So what this result is essentially showing is that, so if you are given sufficient resources to guess and verify the answer to a circuit, okay, so the best you can do is 2 to the minus n unless so the only obstacle to this result could be that NP equals RP. So this result, so this essentially is close to being NP equals RP. So that's the only thing that is preventing a lower bound of the type 2 to the minus n for quasi-linear size circuits. Okay. So one can even, with a somewhat stronger assumption, one can even prove some lower bound on the correctness probability when the circuit size is 2 to the alpha n in the size of the complexity parameter. And I will skip this for now. So the results are fairly easy to obtain once we understand the basic technique here. So let me spend the 5 minutes and explaining the basic technique. Okay. So what we are saying is that, so let's assume we have a circuit family that can decide circuit set with correctness probability 2 to the minus delta n. Okay. And this circuit family itself has bounded resources, and that bound is given by the function f. Okay. So then we show that it's possible to come up with a much better correctness probability by using some more resources, some more time resources. Okay. So there exists a G-bounded circuit family where the correctness probability is 2 to the minus delta square n. Okay. And the size of the circuit is is a composition of f with itself. Okay. So once we have this kind of amplification lemma, so this can be used repeatedly to show that once you have a slightly better algorithm for circuit set, so you can repeat it, and then you can obtain much better algorithm. So thereby you can eventually show that NP has small size circuits. Okay, so that's the key idea.
So if f is just polynomial time, then G is
Right. So, so just to look at the functionality here, what we are doing is that, so there are two resources here. So there are two parameters for the input instances n and m. Okay, and these instances are changing. So n is becoming delta n, and m is becoming the size of the computing circuit. Okay, so we are starting with an instance of size m, and we are going to a poly-size instance, but with a reduced number of variables. And then we take this larger instance with a smaller number of variables, feed it to the circuit in the same family, but to a larger size circuit, and then get an improved algorithm, and so on. Okay. So let me show you the proof of this one, and it's fairly straightforward once we state it. Okay, and it does require a couple of techniques, so what we have here is that, let me go back to this picture. So this is our starting point. So we have this circuit C and M that is taking D as the input. Okay, and it is succeeding with probability 2 to the minus delta n, let us say. Okay, so now we are going to improve that and come up with the circuit family. So G and M. Okay, so G and M operates in the following fashion. So as before, it takes a description of the input circuit, okay, of size m and in n variables, and then it computes the description of a circuit called H, okay, which is satisfiability equivalent to the circuit D. So D and H are satisfiability equivalent, but on the other hand, H has fewer variables but somewhat larger size. Okay, so we are going to take the description of H and feed it to a circuit in the family F, where the parameter S is smaller now, which is about delta n, and the parameter m prime is larger, which is f of m. Okay, and this circuit uses additional random bits, and then finally decides the satisfiability of H. Okay, so since the circuit families F is improving the circuit. Improving the correctness probability, we go from success probability of 2 to the minus delta n to 2 to the minus delta square n. Okay. So the key idea here is that how do we construct the circuit H? Okay. So this is the circuit H. So we use F and M itself. So we use the computing circuit itself to come up with this instance H. Okay. So many of the techniques they use, so they transform one instance to another instance, preserving satisfiability. So in this one, we are going to use the computation itself as part of the instance, and that's where circuits feeding to circuits is important here, and that's crucial to get to this result. And so this is how the idea works. So this is a new circuit whose input bits are which takes delta n input bits. Okay, and it uses a pseudo random generator to blow those delta n bits to about r random bits. Okay, and then the circuit inside takes the description of D as input, which is fixed once for all. So it's specializing to that input, and then it simulates and using the pseudo random bits, it simulates the computation of it simply decides the circuit set of D. Okay. So what exactly is the pseudo random generator here? So what we need here is we need satisfiability preserving one. So in other words, when D is not satisfiable, it's clear that no random bit sequence will produce the answer 1. So therefore we are fine. Okay, when D is satisfiable, so we want to make sure that at least one of the random bit sequence will produce the answer 1. Okay. So where we are gaining the advantage here is that, so previously the circuit families F and M is guaranteeing an increase in the density of satisfying solutions. So let's for a minute look at the circuit F and M and fix the circuit D, okay, and look at the random bits as the input. Based on our assumption, 2 to the minus delta n fraction of those inputs are producing satisfying assignments, provided D is satisfiable. So even if D is uniquely satisfiable, the circuit is guaranteeing an increase in the density of solutions. And we are going to exploit the density by reducing the dimensionality of the problem. Yeah.
So if that pseudo-random function that you're using were replaced by a truly random function, to get the intuition, then it would be exactly like repeating the algorithm to the delta n times as you vary over all the inputs.
Right.
And we already know that amplifies the probability to near 1. So the only issue is we don't have this random function. What kind of pseudo-random function will still have the same property?
So, so this pseudo-random function is an extremely simple function. And let me give you the key idea, which is it's basically Valiant-Vajrani technique applied in the reverse direction. Okay. So what does Valiant-Vajrani do? What do they do? So given a satisfiable circuit, okay, with a certain number of solutions, so they intersect that circuit with random hyperplanes, and with high probability, the resulting circuit will have a unique solution. Okay. So that means the satisfying solution is the satisfying random assignment is satisfying the circuit as well as satisfying the linear equations. Okay. And if you have 2 to the minus delta n, so density in terms of solutions are satisfying assignments, then we only need a system of linear equations with the co-rank delta n. So what we can do is that we can reparameterize the system of linear equations and reparameterize it in terms of delta n free variables, and then rewrite the random variables as linear combinations of those delta n free variables. So what you have up there is simply a Gaussian elimination circuit, or if you want to reduce the size, you can use fast Fourier transform. Okay. So the T basically stands for Toeplitz matrix. Okay. So we basically hash down the number of random bits to delta n bits, because that's what seems to be the dimension of the problem, and then we have a new circuit that preserves the satisfiability but with fewer input bits. So basically we have reduced the size of the set space by a factor delta. Okay. So that's basically the exponential amplification lemma, and so you see how it can be applied. And so let's take a poly-size circuit family and of size m to the k, let us say. So we start with a circuit family that promises 2 to the minus delta n correctness probability and size m to the k. So then we can go to a better circuit family after after d applications of the lemma to a correctness probability of 2 to the minus delta to the d times n, and the size of the circuit m to the k to the d. Okay. So you see the size of the circuit is growing exponentially in the parameter d, but one can apply this constant number of times and get a sub-exponential size circuit. Okay. So that means any improvement in the probability will lead to significantly more improvement in the correctness probability. So that means this particular complexity E, it's either 1 or 0. Assuming that NP does not have sub-exponential size circuits. The same idea can be used. The same application of this lemma can be used to can be used in the case of quasi-linear size circuits logarithmically many times to get much smaller size circuits. Okay. So let me close with a few open questions so you see that we have several results on the complexity of circuit set, several trade-off results, but they all depend on various assumptions. And these assumptions, the stronger the lower bound or the trade-off result, the stronger the assumption is. Okay. So can we weaken all the assumptions to something like NP not equal to RP? That seems to be the fundamental bottleneck to prove lower bounds. That's the sense one gets from these results. So it will be really nice to show that if starting with the assumption NP not equal to RP, we can obtain the same results and perhaps more. Okay. So the second, of course, the more tantalizing question is that can we come up with a better, can we come up with OPP style algorithms for K coloring and Hamiltonian path that succeed with probability C to the minus n, where C is independent of K. Okay. So that, for example, if a negative, so negative evidence to that question shows that that exponential time inclusion exclusion is strictly more powerful than OPP style algorithms. So that means we have separated the algorithmic paradigms. That would be a very powerful result. Okay. So the third direction is that, so here we have not put any limit on the size of the circuit. So we know that 3CN of SAT can be solved better than, with probability better than 2 to the minus n. Whereas circuit SAT may not be solvable in probability 2 to the minus n in OPP style algorithms. Okay. So what is the smallest size circuit for which circuit SAT problem is really hard? Okay. For example, one conjecture is linear size circuit satisfiability is already hard. Okay. So we cannot succeed better than 2 to the minus, with probability better than 2 to the minus n. So proving such a result in stronger models, okay, has a value in the following sense. Remember, one of the goals is to prove specific constant lower bounds on the complexity of these exact algorithms. So provided we can get some results on linear size circuit satisfiability for OPP, then we can start proving lower bounds, specific lower bounds for other combinatorial problems, so at least in the OPP model. So then we will be able to prove 3 coloring must require probability 2 to the minus 0.2 n. Okay, such a result is possible provided we can prove some results about linear size circuit satisfiability. So basically, all these 3 directions will at least fulfill some of the even partial answers to these questions will make progress in terms of proving specific constant lower bounds for OPP style algorithms.